Hello everyone. In this video, we are going to talk about our work, exploiting a joint embedding space for generalized zero-shot semantic segmentation. Recent works using CNNs have achieved significant success in semantic segmentation. But they need lots of training samples with pixel-level ground truth labels, and they are expensive to annotate. Few-shot learning methods have been proposed to recognize objects of previously unseen classes with a few annotated examples. But they still need dense pixel annotations for semantic segmentation task. Learning even without using few annotated examples are called zero-shot learning. And they typically rely on side information for relating unseen and seen object classes. There are two approaches to solving the zero-shot semantic segmentation problem: generative and discriminative approaches. Recent works follow a generative approach that performs well in zero-shot classification tasks. They use semantic features as input to train the generator to mimic the feature extractor's feature distribution. Although generative methods achieve state-of-the-art performance, they have two limitations. First, the visual features of unseen classes are biased towards seen classes. Second, the classifier should be retrained whenever a particular unseen class is newly included or excluded. We introduce a discriminative approach for generalized zero-shot semantic segmentation that addresses the limitations of generative methods in a unified framework. A simple baseline framework of the discriminative approach can be seen as follows. We use two encoders. The visual encoder extracts visual features from images, and the semantic encoder extracts semantic prototypes from semantic features. To make a semantic prototype acts as a center for visual features of a corresponding class, we minimize the distances between visual features and corresponding semantic prototypes during training. Also, we use a cross-entropy loss to encourage visual features to capture rich semantics. We have empirically found that there is a discrepancy between visual features and semantic prototypes. The semantic prototype map shows a sharp transition at object boundaries due to the stacking operation. By contrast, the visual feature map smoothly varies at object boundaries due to the large receptive field of the visual encoder. Thus, directly minimizing the distance between visual feature and corresponding semantic prototypes might degrade performance. Now, we are going to introduce boundary-aware regression loss in a simple yet effective implementation to solve the problem. Unlike before, we first downsample the ground truth mask by a factor of r using nearest neighbor interpolation. We then stack semantic features with the downsampled ground truth mask and obtain a semantic feature map. Then, we upsample this feature map by a factor of r again using bilinear interpolation to get an interpolated one. Using this as an input of the semantic encoder, we can get an interpolated semantic prototype map. Finally, the boundary-aware regression loss can be defined by replacing the discrete semantic prototype term of center loss to the interpolated one. We can interpret this loss as alleviating the influence of visual features at object boundaries, in that this term encourages the visual features at object boundaries to be closer to virtual prototype than the exact ones. We also propose to use a semantic consistency loss that transfers relations between seen classes from a semantic embedding space to the joint one. This regularizes the distances between semantic prototypes of seen classes explicitly. An overall objective for training our model end-to-end as follows. Now let's talk about inference process. We formulate the inference process as a retrieval task using the semantic prototypes as a nearest neighbor classifier in the joint embedding space. As you can see in a figure, although our approach learns discriminative visual features and semantic prototypes, visual features of unseen classes might still be biased towards those of seen classes, especially when both have similar appearance. And this results in misclassifying the unseen class as the seen class. To address this, a recent work proposes a calibrated stacking method that penalizes scores of seen classes with a constant value gamma. We interpret this as shifting the decision boundary of the NN classifier to semantic prototypes of seen classes. It however applies the same value of gamma to the case even if the first two nearest prototypes are close. This degrading performance for seen classes. Instead of shifting, we propose to modulate the decision boundary using the Apollonius circle. This is more intuitive than CS in that visual features of seen classes are tightly centered around corresponding semantic prototypes. Note that the radius of this circle adaptively changes in accordance with the distance between the first two nearest semantic prototypes. We compare our approach with state-of-the-art GZS3 methods on Pascal VOC in context. We achieve a new state-of-the-art on 4 out of 5 Pascal VOC splits. And we can see that our approach outperforms all other methods including the generative methods on all splits of Pascal context. For more information, including codes, please visit our project website. Thank you for listening.